Okay, so for our physical design, I since it's going to be an introductory session today, so I thought I'll discuss the syllabus and what all will be looking in the syllabus for this open elective, and we'll also look into few introductory concepts with regards to physical design. Okay, so one thing that comes into your mind, when we say physical design, which means something where we design and it's in product form where you can feel it, where you can touch it, right? So these days, physical design has a lot of demand in the field of VLSI. Okay, I think some of you are aware of this, and there's a huge requirement for engineers who are well versed in physical design. More or less, it's going to be the same what we did in CMOS VLSI design lab, where we drew circuits and then we checked for errors, and then we came up with layouts, and then we did couple of checks such as DRC, LVS, PEX, back annotation, right? And also we generated the waveforms, and accordingly we were able to judge if the design is proper. How about the delay? How about the phase shift, right? How about the AC characteristics, the DC characteristics? And in layout, we were able to decide the value of resistors, capacitors, parasitic values, all this stuff. So we are going to take this a little further, okay, here in physical design, which means, we are going to actually manufacture the chip before we get into GDS2, which is nothing but your graphical data schematic for information interchange. So before we getting into that, okay, so we will actually decide how the IO pads are going to be placed, what is going to be the distance between the core and these pins, right? So this is what all that we are going to do in physical design. And the other thing that we can look into is the application point of view. So once you know this physical design, okay, you will be able to understand how a circuit is brought into product form, okay, and how it can be implemented as an IC. Okay, so that's all about your physical design. We'll be using a set of tools, set of commands to make our job easier. We'll be running few scripts. Okay, fine. So the course code is going to be 20 NHOP 718A. This is a 3-credit open elective. Okay, and we'll be having about 3 lecture hours, okay, per week, and exam hours is going to be 3. The same model as you have for your regular subjects, right? And CI marks is going to be for 50, and SE marks will be for 50, 100 scaled down to 50, so totaling up to 100. So once we finish this course, we should be able to have these outcomes, these 6 outcomes which we have selected, right? So you'll be able to understand the technology behind VLSI and how this backend design flow happens, right? So basically we have 2 types, the front-end design and the back-end design. So front-end design will be writing a code, be it Verilog or VHDL. And then once we have this code, okay, we will be running it. We'll be checking for errors. If there are no errors, then we'll be proceeding and we'll be getting the waveform. Once we are fine with the waveform, we go with synthesis, we get into the, netlist form, and then, we'll be able to analyze them. So here in backend design, as I was telling you, we don't write any code here, right? We will be designing the circuits, drawing the layouts, right? And from then on, okay, just simple commands will be running, okay, and we'll be generating the files, okay. But basically there is something called script file, okay, where we'll be actually making changes with respect to the placement of cells. Okay, so that is one point where we do coding, but it is not like your regular C, C++ or Verilog VHDL. Fine. So we'll be able to apply the procedure of floor planning in physical design. Now, floor planning is as good as, when you're going to construct a building, you're going to decide where, this section falls, where you're going to have your living room, where you're going to have your dining area, where you're going to have your balcony, right? So you're going to decide in the plan, and accordingly that's going to come up in a product form, right? It's going to come up physical form. So the same thing happens here also. So we are going to decide as to which module, which section is going to be where, and once we have finalized that, then it comes into product form. Okay, we'll be sending it to Foundry, and once we have that ready, okay, once we have the Foundry ready, then once we send the file to Foundry, then everything should be okay. So the next one is use placement algorithms in physical design. Okay, now physical design, as I told you, is a very huge concept. Okay, and there are many things to learn in physical design. So there are a lot of algorithms. Okay, all these algorithms are to optimize, are to make sure that things are placed properly, and we get the most optimized way of dealing with um, circuits. Okay, with the placement of cells, and not only that, you should not have your interference. Okay, if you have your interference, then it's going to be problematic. Okay, it's going to actually hamper the performance of the other sections that are next to each other. So you'll be able to apply placement algorithms. Now again, for floor planning, okay, we discussed what is floor planning. Now algorithms, okay, algorithms for placement. So you should remember that those blocks which are, having too many connections between them should be placed close to each other. That's because, as the wire length increases, the resistance and capacitance also does increase. Okay, so if it increases, then it means that our performance is going down, and we will not be able to have, a better IC, I can say, right? So we always look for performance, and if performance is not good, we will not like to have it, isn't it? Next, we're going to examine routing and design rule check for a given physical design, right? So routing is nothing but the connections that happens between one block to the other. Okay, and we're going to run few checks, few rule checks, okay, as to is this satisfying this particular protocol, is this satisfying the spacing, is it satisfying, or are there any shorts happening. So all this is checked. These days, because of the development of EDA tools, it's making our work much simpler, right? So you can just design it, and then you can check if there are any errors, and you can start working on those errors, right? So it becomes pretty simple. Without these tools, it becomes complex for us to work on things manually. Sometimes, we wouldn't be able to even recognize, um, the errors, right? So with the tools, right, it becomes easy. Fine. So the next one is nothing but evaluating clock tree synthesis, right? So in short, sometimes this is also called as CTS. Okay, there are specific job descriptions. If you can just look into the job portals, right? Physical design, CTS, then verification, okay, testing. So all these things. So this is one among them, clock tree synthesis. So here we'll be looking here specifically into how clock functions, okay, and how is the pulse passing through from one point to another, okay, and how we are able to, manage power in the circuit, okay. Are we able to, have a low power circuit, okay, because that's also important. So engage in independent learning and perform physical design of selected VLSI circuit. So any circuit that is given, we should be able to have a physical design for that, which means we should be able to send it to the fab and get it in product form. So all this will be possible only if and only if we have all these contents gone through. So the textbooks that we are going to use, I have selected 2 textbooks and 2 reference books, okay, out of which the first one is VLSI Physical Design Automation, okay, that is by Sadiq, and the second one is VLSI Physical Design from Graph Partitioning to Timing Closure from Andrew, a very nice textbook. And also you can have J. Bhaskar, okay, this is one of the best for STA, for static timing analysis, okay. Then you can also refer to Michael J. Smith, okay, this is used for ASIC, application specific integrated circuits, where a lot of algorithms are discussed here, right? I was telling you about these algorithms, so many such algorithms will be discussed in that textbook. Fine. So we have split it up into 5 modules, right? First one will be introduction, second one will be partitioning and floor planning, and the third one is going to be placement algorithms, fourth one is routing, and fifth one is how you're going to plan your power. So in introduction, we're going to see how is the PD flow, okay, physical design flow. What are the inputs that you're going to give to PD? Okay, it can be your library files, it can be the netlist, okay, or it can be the design constraint files, or it can be LEF, library exchange files, or it can be the output of PD in the form of GDS2. Then how we are going to check the area, power, timing. Many of these things, you know, we have already seen in VLSI lab, right? We have seen how much of area that it has taken, what is the power, what is the timing, and you know, in the form of graphs, in the form of numbers, in the form of you know, bar charts, all this we have seen. Okay, so the next is partitioning and floor planning, right? Here partitioning is nothing but you have a system and how you divide it, okay. Here we have a circuit and how we are going to divide it, how we are going to, you know, place it across. So that's your partitioning. Floor planning, okay, as I mentioned, which module is going to sit, okay. Then we're going to have different algorithms for that, okay. So it's not only just random placement, but then you will have certain algorithms where you can actually decide, okay, how things are going to work out. So if you have these algorithms put in place, okay, then you know, you can easily work it out. You can probably think of, okay, this algorithm is not working fine, okay, let me shift to the next algorithm. So it actually gives you a clean process, and you can know, okay, fine, that, you know, I'm going to use the other algorithm. If not the first one, I'll go with the second one. So algorithms plays a very important role. Then pin assignments, okay, how pins are assigned. Then floor plan, the die size estimation, the aspect ratio, okay. Aspect ratio is very much important because the width, the length ratio, the beta ratios are all you know, need to be concentrated on. Next, how you're going to use the core, okay, how much of utilization of the area, are you going to use 60%, are you going to use 80% of the core, okay. That is where your transistors are going to be placed, okay. Then about macros, it can be soft macros, hard macros, okay, or firm macros. So we will be looking into them in detail. Next, with respect to placement algorithms, okay, we are going to look into simulated annealing, force directed, okay, and Brewer's algorithm. So these are 3 algorithms that will be concentrating with respect to placement. Then types of placement, is it standard cell? Okay, basically what's a standard cell? We're going to you know, where FPGA can be considered as a standard cell, right? where you can have multiple things done on it. Then you have the building block placement cell types, which is well tapped cells, end tap cells, decap cells, filler cells, spare cells. So how we are going to utilize the area which is available um, for the utilization, the core utilization, how we are going to use it, how we are going to place it, um, because we shouldn't leave any free space, right? Everything should be occupied, and not only occupied, there shouldn't be any interference between them, right? So that's also important. So next we look into timing driven placement. Okay, how timing plays an important role. Then congestion. Okay, the same thing which I told you about the interference, right? So there shouldn't be any congestion. Things having too many connections, okay, can be placed close. If you place it far, then these wires have to run for a longer distance. Okay, so that will in turn cause reduced performance. Next, placement congestion, global route congestion, congestion map, and how you ease your congestion. What are the ways that in which you can ease them? Now, with respect to routing, you have grid routing, global routing. Okay, routing is nothing but these connections that happens from one model to another, right? And design rule checks, DRCs, clock route versus signal route. Then shorts, are there any shorts? Then opens, okay, any open path. Then routing signals in higher layers. So as we just don't have metal 1, metal 2, metal 3, but then we have way up till 8, 9, 10, right? Different metal layers. So it's going to be like a sandwich, right? One on top of the other. So how we are going to utilize them? Getting attributes like route length, number of vias, etc. for a given net. Next, with respect to power plan, okay, we are going to see how many strips we are going to use, how many rings. These are all power rings, okay, power strips, power rails. Next, how is the power management happening in the core? Okay, then how are IO cells placed? Because whatever pins that are placed should be connected properly for communication. Next, IR drop, right? How much of drop is happening? What are the types of drops? Latency, jitter, okay? Then early clock tree. Before you finalize, you're going to do a pre-check and you're going to see if anything is not aligned. Then skews, then hold fixing function mode, shift mode, with respect to clocks, false paths. Okay, so there cannot be any connection, but then it will generate few connections, so false paths. Then clock routing, NDRs. Okay, so we'll be looking into them one by one, and we will see how it goes. Okay, so basically physical design is into placement, okay, placement, routing, okay, floor planning. So all this stuff comes into picture. So floor planning, placement, and routing. Okay, so first comes floor planning, next placement, and then routing, and it goes on. It gets optimized like a loop. Okay, so if it's not fine, then again you go back, you do a new placement, and then you check if everything is okay. So we'll look into a few basics, okay, into VLSI design and what the technology involves. So what is enabling us to move into physical design? Okay, so these are some of the best textbooks that you can refer with respect to VLSI design. One is going to be Pucknell, which is basic VLSI design, very nicely written. And there's another one called CMOS Digital IC Design, Circuit Analysis and Design by Kang and Jan Rebe, which is Digital IC Design. For references, we'll be using Veste, okay, Principles of CMOS VLSI Design. I think you have used this second edition. Right now, there's
fourth edition, yeah. So, and additional reading you can take up from journals or papers. So why do we want to design VLSI circuit is the first question. So basically these days everything is going digital, isn't it? So we are moving away from analog design, and we cannot fully get rid of analog, right? Because that's the core. But then digital is making our lives more simpler, right? Just if you compare an analog clock and a digital clock, right? Analog you'll have to see, and then it takes some seconds, some microseconds for your brain to process. But then digital, as soon as you see the clock, immediately the numbers pop in. So it's easy for you to recognize. And even though people who do not see, small children, for example, even if they don't know how to see time, they will be able to, right, with the help of digital. So it's all becoming zeros and ones. So which means it becomes easy for us to process things. So realization of complex circuits using discrete devices are difficult and very costly. So we want to make things more simpler, right? We want to make things more easier. Okay. We want to make things less cost effective, right? So which means I should spend less but get more out of it. IC solve this problem by printing all small circuits on a single flat surface, right? So integrated circuits, you'll be able to print it just like your PCB, right? The connections, the paths are laid out. So this reduces the cost because cost depends on die size. Now you should think of, Moore's law. So in Moore's law, they say, it states that every 1.5 year or 18 months is going to be the number of transistors doubling on a wafer. So let's say, about 1.5 year back, if we had about 100 transistors, then by now, post 1.5 year, we should be having about 200 transistors. So the number of transistors on the wafer is doubling for every 1.5 to 2 years. So that was the basic trend that was observed by Gordon Moore. Okay, and that is one of the most referred statements. Thus, VLSI design manages complexity and helps to simplify complex design problems, right? So not only recognizing, but then we are able to design things, right? So that's important. It determines efficient solutions in terms of area, power, time, and performance. Now, these are very important, right? With respect to area, less area, more transistors, less power. With less time, I should be able to manufacture it, and my performance should be very high, right? So all these have become our basic criteria for any circuit that we design. It can be a simple circuit, it can be a complex circuit like amplifiers, right? So we want things to consume less power, and we want the performance to be as high as possible. Okay. So a little bit of history as to how these ICs evolved, right? So in 54, we saw first silicon transistor. It costed about $2.50. Then in 61, the first IC, okay, which was a flip-flop circuit, cost about $50. Then from 61 to 66, SSI came into picture, which is nothing but small scale integration, where few hundreds. In MSI, few thousands. Okay, and in LSI, like about 10,000, 20,000. VLSI took it to the next level, right? Close to 500, close to 100,000. Then after this we have ultra large scale integration, ULSI. Of course, I have not put it up here. So in SSI, you have about 90 to 100 transistors. Okay, flip-flop gates. Similarly here, 100 to 1,000. hear about adders, counters, 1K RAM chip by Intel. So this was all done in between 67 to 91. Then 72 to 78 was LSI, right? Where it started about 1,000 to 20,000 transistors. So moving on, 78 to 88 in the 10-year span, you can see 20,000 was the max, but here they've moved on to 500,000. So which means, things started moving rapidly. Okay. And they were able to integrate more number of transistors, thereby increasing the functionality, right? So you can imagine the watches, the analog watches that we had previously, right, which was only showing time. That's it, nothing else. Then slightly they integrated it with showing date. Okay. Then slightly they integrated it with showing day, right? Then slightly they integrated, separate multi-dial, multi-dial type, where time is shown separately and then seconds are shown separately, a small clock. So it's like a multi-dial, and then day was shown separately. So there was a kind of evolution that is happening. And these days, you have these smartwatches which are even capable of taking your ECG, right? So things have become very complex, but then simple to use, right? Internally, they are complex. They can even check how much of oxygen that you have in your blood, right? Based on the color of the blood, what is the pulse, right? So if you can imagine the history of watches, right? Many things have evolved. So all this is possible only because of VLSI technology, right? So because of these incremental change that has been happening since SSI to ULSI. Okay, so here they had microprocessors and sophisticated peripherals. Fine. So you can just see, right, the feature size. The feature size is nothing but the channel length. Okay. You can also say that's the technology, 180 nanometer technology. These days you have transistors having channel length of 3 nanometer. Processors are in the pipeline. The next set of processors that are going to come is going to have 3 nanometer channel length. Okay, nanometer, nano itself is 1 into 10 raised to minus 9, right? So 3 nanometer, right? So it's the space between the source and drain is very less, right? Okay, so as you can see, 180, 130, 100, 70, 50, 35, right? So way back in 14, we were able to have 35. That's the feature size, nanometer. Next, if you can think of, the transistors, right? Phenomenal increase, right? You can just see from 39, from 1839, 84 million, right? 180, 390 million number of transistors, right? Then you can see this number of pads per chip, number of clocks. Remember, I was telling you the IO blocks, the IO pads, the placements, right? So from thousands, from few thousands, it has gone up to 10,000s, right? Then you can see clock is phenomenally increasing from 1.2 megahertz to 16.9, 16,900 megahertz, right? So it is more than 10 times of the initial 99 year. Then chip size, you can see chip size is increasing, okay, wherein you are able to integrate more transistors. Wiring levels, I was talking to you about the sandwich, right? One layer on top of the other, and then on top of the, just like an apartment, right? Single area, okay, but then you have multi-story building. So just like that, you can design your IC. So you can view that properly in a 3D view. Okay, you can move it, you can zoom it, and then you can see how this wiring goes from one layer to another. So wiring levels have phenomenally increased from 6 to 10. This was way back in 14, but these days, this has changed a lot. Then power supply, okay, it has come down to 0.5, okay, in 2014. So as the channel length reduces, you don't need much of power to activate it, okay, because it's becoming more small, and the food required, the VDD required for these transistors is reducing. So because of which, they're able to operate at lower voltages. So if you can see, your power P is equal to, V into I. So directly, if you can reduce the voltage required, okay, so ultimately your power drastically reduces. So they become more power efficient. You do not want a smartwatch which just lasts for about 1 or 2 hours, and then again you need to charge it. No, I don't think so anyone would purchase it, right? You would probably need for a decent 1 day at least of heavy use, no matter however you use, at least 1 full day you should be able to get, right? So that is what is expected. So all that is possible only with, keeping low power in mind. So high performance, right? High performance. Uh, Power is, slightly increasing, 175, 183, right? The power requirement. So there is a lot of demand for low power. Okay. So as the power reduces, the heating also reduces. As the heating reduces, the usability of this transistor increases. So which means you can use it for longer time. See, whenever it is exposed to heat, anything gets damaged. Okay. So here, when it starts operating, there will be a lot of heat or power dissipation. Power dissipation will be in the form of heat. So thereby indirectly damaging your device, right? So low power is actually very important when we think of circuit designs. Okay, so you can see this in the graphs here, right? Starting with 4004, okay, Intel's first IC, integrated circuit, in 1971, right? So the power requirement you can see here. So it's not even touching 1 watt, okay? And then, you can just see the graph moving on. It's never been stable, right? So you can see that, it has reached here 100 watts, 500, 1.5, okay, 18 kilowatts, right? So which is huge, very huge. So if you have to sustain this much of power dissipation, you may have to have a regenerative circuit. You may have to have a circuit which actually conserves this energy. You may have to have a cooling circuit which can, bring down these temperatures. Okay. So if you can see here, for in 2008, right? So there were circuits, there were ICs which actually touched about 18 kilowatts. Okay, so power delivery and dissipation will be prohibited. So this data is from Intel. I picked it up from Intel way back from 91 to 2008. Okay. Now, with respect to complexity and the years, okay. So here you can see that, the green line here suggests the logical transistors per chip, and the red one, it refers to transistors per staff month. Okay, how much it needs. Okay, so 1981, okay, about 10 logical transistors per chip. So if we go down to 2009, okay, so that's about 10 crores, right? So it's all in billions now. It's all in billions. So billions and billions of transistors are being packed. How is it possible? Because they've made them small, right? So if 4 of you are able to sit in a bench, okay, now they're able to place about, say 10 of them in a bench. That's because, the size is reduced. So if the size is reduced, the area required the space required to occupy in in the wafer is less. So whereby you can actually put in more transistors. Now the other best part is that you don't have to worry about the power dissipation, okay, because there are specific set of engineers working exclusively on power, okay. So where they analyze, where they try to find out what kind of metal to use. If suppose some material is not fine, okay, then they will change the material. Did you know that few of these supercomputers, the chips that they manufacture for them, the wiring is made with gold internally, okay. That's because it's a good conductor, it doesn't rust, and whatever information is passed immediately uh, gets passed from one point to another. So which means here you can see metal selection also plays a very important role, okay. But then we cannot have gold in every chip, right? If not, the cost would shoot up, and the availability of gold is challenging, right? And we cannot keep the cost minimum, right? So moving on, many disciplines have contributed to current state of art in VLSI design. So there are many things which have contributed. It's not just the engineers, it's not just the technology, but many other things which have supported this migration, right? The first and foremost is the physics, right? Solid state physics. So you should understand how this IC works, okay. You should understand how this electron migrates from one point to another, and how they are able to catch up uh, with respect to potential difference, what is happening to the spin of electron, okay. And when they bombard, what is happening, how is the channel getting formed, right? All this is nothing but physics. So deep deep material physics is something which is which is not taken up by many people, right? Solid state physics. Next, material science. As I was telling you, aluminum also is a material, okay. So then steel also can be a material for connecting things. Copper also can be, gold also can be, right? So a lot of research and development in the field of materials, and finding out how they pass information, how they can transmit information from one point to another, plays a very important role. Lithography and fabrication, right? So lithography, this is nothing but about the wafers, and how these wafers are manufactured. Actually, you should see a video on how these chips are manufactured from sand to chip, okay. There's a beautiful video by done by Intel, okay. You can just look into it. I'll be posting that link as well for you all to have a look at it, okay. And device modeling, okay, how we are able to model the device, how we are able to target the power dissipation, how we are able to convert from a circuit to layout, all this stuff. Next, architecture. What kind of architecture that you're going to use, how you're going to connect the bus, how is the routing employed, okay. All these stuff comes in architectures and algorithms. So different tools, okay. Three major software providers: Cadence, Synopsys, Mentor Graphics, right? Three major software providers for VLSI industry, right? So each has its own crown. Mentor Graphics is good at something, and Cadence is also good at something. All are not good at everything, okay. So that is one point that you should remember. So the industry uses different set of tools offered by these EDA companies for running different tests, okay. So it's not that they're just dependent on one software, they depend on different softwares for running different simulations. Next, circuit design and layout, right? As we all have done in our laboratories, right? We draw a circuit, and then we check for errors, and then we see if the circuit is fine, or we try to make some modifications in the W/L ratios, and probably we're going to reduce the
wire lengths, we're going to get it closer, right? We're going to check if the ports are fine, and we're going to simulate it, check for waveforms, and then accordingly we move on with various checks, right? Design rule check for the layout, right? And then here in the circuit, we check for errors, and then we check for waveforms. If the waveforms are satisfactory, then we move on to layout, and we have different checks there, right? Okay. So MOS physics, okay. So why do we need MOSFETs? Okay, MOSFET is nothing but your metal oxide semiconductor field effect transistors, right? So field is needed. Field is nothing but voltage, right? Potential difference is needed, and we have an oxide there, which is silicon dioxide. Semiconductor is nothing but silicon or germanium. Okay, metal that we use is aluminum. Metal oxide semiconductor field effect transistor, right? So that's the meaning of MOSFET. So CMOS circuits dissipate power only when switching. They do use power when not switching, but it is much less than other circuits. So that's why we have selected MOSFETs only during operation. Okay, only during operation, MOSFETs consume power. And when they're ideal, okay, when they are in their ideal state, uh, when they're in their static form, right, they do not consume any power. So even if they consume, it's very less. That can be in the form of leakage. So this allows for more circuits to be placed on one die. Okay, so that's why scalability is also one such option that we have with respect to MOSFETs, right? We are able to scale down the transistors and keep as many as possible. So hence we have migrated, from BJTs to MOSFETs. Okay, so how is the design flow? Okay, so we're going to look into a few definitions and terminologies, and we're going to see about the Y chart. Okay, so abstraction, refinement, okay, extraction, generation. Okay, so we'll be looking into them one by one. Design process traverses iteratively among three domains, which is shown in the Y chart. Okay, so there are basically three domains, three important domains. Okay, and we can see this in the Y chart. So the first one is physical domain, the other one is behavioral domain, and the third one is structural domain. Okay, so these were the words that we saw there: extraction, generation, refinement, abstraction. Okay, so there are various things involved here, okay, in the Y chart. So something that covers between behavioral and structural is system synthesis, okay, and logical synthesis, circuit synthesis. Okay, something that comes in between structural and physical domain: transistors, gates, flip-flops, registers, ALU, processors, bus. Okay, and something that goes only in the physical domain, okay, is nothing but your transistors, layouts, chips, boards. Okay, then only the one that goes into behavioral domain is your flow charts, algorithms, register functions, Boolean expressions, and minimizations, optimizations using K-map, Quinn-McCluskey, and transistor functions. Okay, so all this is nothing but refinement. Okay, refinement. So transistors, transistor functions, gates, flip-flops. Okay, so Boolean expressions, that is logical synthesis, registers, ALUs, that is RTL synthesis, right? Register transfer. Then flowcharts, algorithm is at the system level. Okay, so where you have processors and buses when we talk about structures. Okay, so a very important chart, okay, having a lot of meaning in it. Okay, transistor, Boolean, RTL, flowchart. Okay, so first is going to be your circuit level, okay, logical level, RTL, system level. Okay, so that's how it goes. So this is a simplified version, okay, of how the flow happens in all these three domains. So what are those three domains? Structural, behavioral, and physical.
Okay. So first we're going to have system specifications, right? So after that, we're going to move on to functional specifications. Okay. What function is it meant to do? Then you'll have verification of whatever specifications is there. Okay. Then you move on to logical design. Okay. So this behavioral is given in red, right? So these two are behavioral domain. Then 1, 2, 3, 4, these four move into your logical domain. Okay. And the layout will be your physical design and verification, right? So moving on, you have logical design. So whatever you design, you need to verify it. Once you're fine with that, you can put it in the form of circuit. Okay. And you verify the circuit. You have a physical design for that. Again, in physical design, you know, there are a lot of checks, right? There are a lot of checks that happens, DRC, LVS, parasitic extraction, back annotation, many things happen here. And then, you know, that's where verification happens. So these two can be called as behavioral domain. Okay. And then structural domain, and these final ones are called physical domain. So Y chart, and this is very important. Okay. So you'll be able to understand, okay, how these three domains work: behavioral, structural, and physical. So these three, you know, consist of the major domains: the behavioral, structural, and physical domain, as we saw in the Y chart. So moving on, VLSI chip design styles. So basically there are three types: full custom, okay, standard cell design, and gate array, which is nothing but your FPGA. So FPGA, I think all of you have worked on it, right? Multiple applications can be, can be run through. You want to function it as a counter, it can. You want it to work as an adder, yes, it can. So based on the program, you dump it on the FPGA kit. Next, your standard cell. These are all standard blocks, okay, wherein you just take them and place them, right? You're not designing them, you just get them off the shelf, right? Full custom is something where, you know, you design from scratch. You go to the drawing rooms, okay, you design the circuit, you design everything right from scratch. So that is your full custom. There's a downside for full custom, right, where you cannot have control on cost, okay, but performance is going to be the highest. And if we compare standard cell, right, you can build it fast, but then performance cannot be as good as full custom and FPGA as well, right? So you cannot expect, okay, both time and performance to go hand in hand. Okay, usually they are indirectly proportional to each other. The more time you spend for designing, this full custom design, for example, the higher performance you can expect, right? Okay, so this is what, I was telling you about, the pad rings, the IO pads, right? So this is going to be the core that you are seeing, right? So in this core area is what we are going to have: logical cells, the channel, routing channel, okay? And then again here, these are all logical cells and channels in between. So this becomes your core, okay? The one that you see in your square. And these small squares that you see around is nothing but the connection to the outside world, right? So these are IO pad cells. Now, if we dive deep into it, right? This is an example taken for FPGA, right? This is the same IO block, right? So this is your horizontal routing channel, right? And this is your vertical routing channel. So vertical routing channels are given in blue, light blue, and horizontal is given in red. Okay, so these are all your cells, the logical cells, and how you connect between them. Say, for example, you want to connect, this this block with this block here, Okay, so you have two ways, either you come in this way or you come in this way, right? So worst case is going to be connecting this block and the final block here, right? So the one which is here is nothing but your configurable logic blocks. So which means whatever program that you're writing and dumping comes and sits here. Okay, so these are nothing but CLBs, configurable logic blocks. Okay, so standard cells. Okay, these are where your base cells or logical cells sit, and this is your routing. Remember the previous diagram that we saw, the logical cells, routing channel. Then again comes logical cells and routing channel. Okay, so standard cells, then the routing. Okay, so this is one such way of arrangement, and these are nothing but your IO pads which are placed along. Now full custom design. Okay, let's look into it for a while. So complete fabrication process, you're exactly starting from the scratch, and then you're sending your designs to the fabrication center. Okay, so manually you're doing everything, right? You're not depending on any shortcuts. Then there's a lot of flexibility involved here. Okay, so because you're the boss of your circuit, you can design it however you want. It's not that you're depending on some other design where you do not know how it's actually made and you do not have the flexibility to work on it or to refine it, so to say. So here very high development cost is needed, right, as I told you, but then the performance is going to be high. Longer design and fabrication time, so time taken for designing is going to be higher, but there's going to be a good use of silicon area. So once you have good use of silicon area, it means that you're trying to pack things um, to an extent where it doesn't suffer losses. Okay, and then it's cheap only at highest quantity. So if you're just producing say about 100 500 types products items, then it's not going to really work out for you, because the cost that you have spent for the engineer to design, the cost that you have spent for testing and verification, always remember about 80% of the time goes in 70 to 80% of the time goes in testing and verification. Whatever that you have developed, right, you need to check and you have to verify if it's fine or not, and then only proceed. Okay, so that's how it is. So if you can produce it in bulk, okay, then only you're going to see a slight amount of profits. So that's in full custom design. So many companies who wants to differ from the other regular companies, they try to go with full custom design, where they want to design everything from the scratch. They do not want to depend on something else, and they want the best performance. So that's why you see few products are pricier. That's because they have invested a lot of research on it. They've invested a lot of development on it. They've invested a lot of engineer working hours on it to refine the circuit. So full custom, you have the top view, right? I think all of you know that your transistor has wells, right? And well, P well, okay, polysilicons, the diffusion layer, N plus diffusion, P plus diffusion, the body, substrate. Okay, so I hope all these are clear with you. If not, then probably I can take a session on the basics of the transistor, the cross-sectional view, and the characteristics, probably in our upcoming class. Okay, so this is the top view. Okay, how you see the metal wire, right? The same thing that we used to do it on the software, right? So how it's connected from one point to another point, right? And these are the contacts, right? Contacts. So this is the top view. This is the side view, or how you can see from the front. Okay, so you are trying to connect from one point, you go up, and then you have another metal here, and then slightly you come down, right? So if you can see this from front, okay, this becomes your cross-sectional view. But then if you are seeing this from top, so this particular area is here, okay, and these two you cannot see because it's top view, right? It is actually sitting below this. This point is here and this point is here, so you cannot see these these vertical lines, right? Okay, So why do we use CAD technology? Because it can give us high level of synthesis. By the way, what is synthesis? It's the next level of simulation. Simulation is something where you get the waveforms and then you check if your inputs and outputs are fine. But then in synthesis, you are getting the text form into graphical form, right? Into a gate list form or netlist form. So logical synthesis, it gives me circuit optimization. It tells me, where is the junction that needs to be concentrated on, all that, with the help of software. Then layout, we are doing simulation, design rule checks, formal verifications. So, this is why we are, developing software to actually help us in getting things worked out fast. Okay, so I hope all of you have understood, right? So this was just a quick review as to how or what is actually motivating us for physical design. Okay, so in my upcoming lectures, I'll be discussing few more concepts. Maybe we can dive deep into it and we can understand why this is done. Okay, transistor level we can go with the physics level, okay, and understand why it's happening. And then slowly we can jump into a regular syllabus and we can complete whatever that I have planned, 5 modules, whatever I have planned, we can try and complete it.